In this video, we're going to take a look at ideal gas law with density problems. So I'm going to show you a long way first, and then afterwards we're going to see how to derive density formula using the PV is equal to nRT formula. So just a little reminder when you're doing density, so I'll write D is equal to M over V. In reality, the symbol for density is this symbol over here, like a little P or rho value. That you would use, so you might see that in certain resources, but for the most part, I'm just going to refer to it as D. So density is equal to M over V. And so our main steps when we're asked to find the density of a gas is to assume 1 mole of the substance, then you find the volume using PV is equal to nRT because we assumed 1 mole, and we'd be given everything else, of course, and then find the molar mass of the compound. Now, since you assumed 1 mole, well, the molar mass will end up being your mass overall. And then finally, just do mass divided by volume. So let's go ahead and see what that looks like. Calculate the density of methane, CH4, in grams per liter in this case, at STP. Now, when you're using your PV is equal to nRT to find density, you're going to get it in grams per liter instead of grams per mil, but you could always convert afterwards if you wanted to. The reason you're getting grams per liter is because your volumes for the PV is equal to nRT are in liters. But again, let's go with our first step, which was assume 1 mole of the gas. And the reason you can assume 1 mole is because the density should be the same regardless of how much you have. And then now we can find our volume. So we have PV is equal to nRT. So we can do that the volume is equal to nRT over P, which is going to be 1 mole, which we assumed. We assumed 1 mole, multiplied by our 8.314 kPa liters mole Kelvin, times our temperature. Remember, temperature for STP, we're at 273.15 Kelvin, 273.15 Kelvin, over the pressure, which is 101.325 kPa. Cancel out kPa there, cancel out kPa here, cancel out the Kelvin, cancel out the moles, and we're left with liters, which is what we expected. So 1 times 8.314 times 273.15 divided by 101.325, and you get approximately, I'm going to write all the digits down, 22.41272243 liters. Now, that there is our volume, and it's interesting. This works out to our molar volume. Remember, 1 mole of any gas at STP would be, well, 22.41272243 liters. So if you remember your molar volume concept and you assumed 1 liter, you could have skipped all these steps here, and you could have simply said, if we're assuming 1 liter at STP, therefore 22.41, 22.4 liters is what our volume should be. So that's roughly what we get there, which makes sense. And we need to find the density. Now, remember, for density, we need the mass and the volume. And we want to find our density. We're going to do this in grams per liter. So we have our volume. We just need the grams now. Remember, we assumed 1 mole of CH4. So to find the mass, we do our moles times our molar mass, which is 1 mole times the molar mass of CH4, which is your 12.01 plus 4.04, 16.05 grams per mole. Cross out moles, and you get 16.05 grams. So we have our mass, we have our volume. So now we simply have to do that the density is equal to mass over volume, which is going to be 16.05 grams over the 22.4 liters. I'm keeping all my digits in there though. So divided by 22.4, whoops, 0.41272243, and we get 0.71 0.61113 liters. Now, the sig figs are a bit tricky here because we didn't really give you much information other than STP. So we're going to go and assume that the STP stuff is our sig figs, and smallest number of sig figs we could do is 273.15. So that's 5 sig figs there. So we can say about 5 sig figs that we can use. I don't think anything else was given to us directly. No. So we'll say about 5 sig figs. So approximately 0.7161. Whoops, and it's not liters. I made a mistake there. It's grams per liter. So grams per liter there. Now, if you assumed 1 mole, you made the assumption that you have exactly 1 mole. So you wouldn't necessarily use that in your sig fig values either. So this is your most appropriate answer to the number of sig figs because we're defaulting to the STP values that we're providing there. We're assuming that someone had to measure these values, and so there might be some error in those degrees. If so, it varies on what's given to you in the question. We just defaulted to using the 5 sig figs, and I think I put 4 sig figs here, so I need 71611. One more there. So that was a longer way to do this. There is an easier way. You could actually find the formula for density. So you know that density is mass over volume. We know that. And that's part of what density should be. Mass over volume. Now, if you want to find mass, a little reminder is that your mass is equal to moles times molar mass. And so what I'm going to do is I'm going to take this equation here and rearrange it. I'm going to get my number of moles is equal to my mass over molar mass. Okay, now watch this. I'm going to take this and put it into my formula here. So this is my step 1. I'm rearranging this. Step 2 is PV is equal to nRT. I'm going to replace the N by MRT. So M's in their mass over the molar mass because molar mass is at the bottom dividing there. Okay. Now, remember we said that density is mass over volume. I can rearrange this formula to get mass over volume. That's my third step there. So I can do I can send the M up there and the RT down there and the V down there. So I'll get something like this. I'll get mass over volume is equal to PM over RT. So pressure times molar mass over the gas constant times the temperature is equal to M over V. M over V is density. That's what this is. That is density, right? So if I can use this equation instead of doing all those steps, and I should get the same density. Let's try it out just to see if it works out. So I'm just going to show you that's our second step. You can use this to get the density as well. So we can say density is equal to pressure molar mass over RT. And so we'll get the pressure was 101.325 kPa, so 101.325 kPa, times the molar mass, which was 16.05 grams per mole, divided by the R value, which is 8.314 kPa liters per mole Kelvin, times the temperature, which is 273.15 Kelvin. So 273.15 Kelvin. And notice we'll cancel things out. Kelvin will cancel out. Moles will cancel out. kPa will cancel out. And we're left with grams per liter. Grams per liter. So when we're finding density with this formula here, it's going to be in grams per liter because our volume is in liter. So this is in grams. This is in liter here. And so let's go ahead and plug all this in and see what we get. So we get 101.325 times 16.05 divided by 8.314 divided by 273.15. And we get 0.7161113 grams per liter, which is what we got with the long method that we did earlier. So this is another method you can do it. The long method is the same thing as this formula. We just did it in a series of steps. We're showing you the logic behind this, but regardless of which method you want to use, they would both be correct. So if you use this method here, you'd be good. If you did this method over here, you'd be good as well. So now you know the formula to find density and how it was derived. In this lesson alone, include all the videos we've seen how to derive formulas for a variety of things using some formulas that we already know. You can substitute different formulas into a certain formula to rearrange it and get something that you're looking for, like density, for example, like molar mass, for example. So this is your formula for density when you're dealing with gases, except remember that your density is going to come out as grams per liter because your volumes are in liters when you're using your R value there of 8.314. So in the next video, you're going to do another example, a few other examples with density. Again, you can try them yourself first, and afterwards, you can check your answers in the videos.